we're going to do the next lesson. It's radical functions and transformations. So really, our first step in understanding a radical function, really which a radical, high school students often interpret as a square root, but radicals often imply any type of root situation. So let us construct a function, y is equal to the square root of x, using a table of values. So it might require a little bit of forethought what x values to choose so that we get nice y values. So I'm going to press pause here. I want you to think of some x values that you would use to construct nice y values. With just a little thinking ahead, we look at a function, and the function is, we're going to take the square root of an input. In other words, what inputs square root nice? Well, perfect squares. So that's why I'm going to choose 0, 1, 4, 9. Now, these are not mathematical language, square rootable. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So I'm just going to graph that as a function. I put my points down. There we have it. Now I'm going to connect the dots. And ladies and gentlemen, that's what the square root function looks like. Let's important note, you may be wondering, why did it start here? Well, really this boils down to the equation. If x is negative, you cannot take the square root of a negative number in the real number set. So really, let's make some notes about this. I'm just going to zoom out a bit now that I have this nice picture. Some notes are the domain. X exists such that x is greater than or equal to 0, where x is element of the reals. In other words, in interval notation, we may want to say that the domain goes from 0 to an infinity. Nice square bracket there. The range is also, now if you think about this, this might make sense. The range is y is greater than or equal to 0, where y is element of the reals. So, in other words, if our input is 0 or positive, when we take a square root of non-negative numbers, the output, or the y values, is also positive. Really important attribute is this endpoint 0, 0. It's going to help out immensely in transformations. So let's scroll down here. Let's consider the above function. Y is equal to the square root of x. Let's graph y is equal to the square root of x minus 2. So first thing, I'm going to graph my square root function. There you have it. I have graphed my square root function. Now, I'm going to take a look at this from a transformation point. So here, h is equal to 2. So really, all I have to do is shift the square root function 2 units over to the right. So allow me to do that. 1, 2, 1, 2. Oh, this one falls off, 1, 2, about there. But regardless, look what happens on the graph. And if by looking at the graph, I see that the domain is going to be x exists such that x is greater than or equal to 2, where x is element of the reals. And my range is going to be y exists such that y is greater than or equal to 0, where y is element of the reals. So that's from a graphing perspective, we understand the domain and range. Let's go back to the equation. For what x values will this be valid? Well, I know, let me look at my radicand here particularly. This, I can take the square root of anything that's non-negative. So I'm just going to work this out. In other words, what x values, which is a descriptor of the domain, right? The x values that are permitted. So x values, so in other words, my radicand has to be greater than or equal to 0. If I add 2 to both sides of this inequality, x has to be greater than 2. So that might be a good solid explanation of my range that I see on my graph, or my domain that I see in my graph. My range can just be thought of, well, all this is going to be is 0 and positive. The square root of anything 0 and positive, well, any number in that domain will just be positive. So that is also my range. Now that I know that's a little bit harder to see. So there, and what we see is reflected here. Now let's focus our attention on the next one. Where do you think we're going to start off? And in fact, we're going to start off with y is equal to the square root of x. So I'm going to graph that. Let us graph. There is my function. So right now I can take a look, and since I'm pretty clever, since I've taken transformations, I can see that this k is just simply 1. In other words, all I have to do is to take my x value or my y values and I shift them up 1 unit. And that's fairly straightforward, I think. Oof. Right, you have a ruler, I'm hoping, or not a ruler, you don't need a ruler, but hopefully better eye-hand coordination than I do on the stylus. So important to note that we put an arrow at this end and a solid dot at this end. The solid dot just simply means my function ends. So solid dot just simply means my function begins right here, and the arrow means that it's continuous all the way to the right. If I take, so from this, we're able to see the domain and range. So write down the domain and range, and I'll quickly do it. Just look at the graph, and then we'll try to pick apart the algebra equation, or the equation for the domain and range. From the graph, I get my domain as x is greater than 0, and my range as y is greater than 1. But from my equation, I know I can pick this apart right here. I know that y is equal to the square root of x. Now I'm just going to maybe write this in interval notation. So this function will have the domain 0 to infinity and the range 0 to infinity. So if we just simply add 1 to the function, shift it up 1, the domain stays the same, but the range increases by 1. If we're moving down the page, how is each graph compared to the original? I would just argue each graph is just a shift of the original. And I'm sure that we're going to get into reflections and stretches, but right now we're just a shift. So here is an important idea. Why do we do transformations? So we can think about functions in a different way, and transformations really help out. At times it's important to keep in mind where the parent function or f of x is equal to x squared, and just ask, how is the parent function being transformed? This may inform you of the domain and range of the radical function. So let's move on to this. Sketch the graph of each transformation using, or of each function using transformations. Compare the domain and range of the graph f of x and state the changes. Okay, so what I'm going to do here is, here's f of x. I'm going to build this up, applying each transformation. So first things first, I suppose, I need to identify what my transformations are. In other words, I need to identify A, B, H, and K. Please do this. I think it's pretty straightforward to pick out A, H, and K here. So first things first though, I hate this thing, B. So what I see is the coefficient in front of the x is 1, so it's already been factored out. So in here, A is equal to 3, B is equal to -1, H is equal to 2. All right, shall we start? Now, with the transformation, A is equal to 3. So I'm going to write a little blurb about this. A is equal to 3. This is a shift. Sorry, not a shift. There's a lot of bad with that statement. So this is a vertical stretch by a factor of 3. And so for instance, I take we start off with point x, y, and here it's x, 3y. So that would take care of the A. Now B, I'm going to switch to maybe blue, hopefully, blue. So there's one transformation I need to do. B is equal to -1. This is a reflection about y-axis. So it takes point x, 3y, and changes this to point -x, 3y. Now I'm going to maybe move into green. So h is 2. So this is a horizontal shift two units to the right. Okay, so I'm going to try to go through this fairly fast, and I would like you guys to select the color that corresponds to the vertical stretch. Here I've chosen red. There we are, red. And I'm going to do it. I'm going to vertically stretch by a factor of 3. How about you do it? Let's do this. I mark out the points that I know. Those are the points that I know. And I simply multiply the y values of each point by 3. There they have it. My transform graph. There should be arrows here and here. Now I'm going to reflect this about the x-axis. So these points here, that my new points, I'm going to reflect them about the x-axis. So these points, simply I'm just multiplying the x values now by -1. Have it. So 4, 6 becomes -4, 6, 9, 9 becomes -9, 9. Now I'm going to connect the dots. Now this is where it starts, right? There we are. So far, not so bad. There is my reflection about the x-axis, and I'm just going to exaggerate these points for you. They're just simply making the x values negative. Last but not least, I am going to move each point and my curve 2 units to the right. So I can do that. So I move this 2 units to the right. I move this 2 units to the right. 1, 2. In other words, I guess I should put this in point notation. -xy, I just simply add 2 to the x values. And there we have it. There is my resulting function. So I'm just going to take a bit of a break right now. I'm going to press pause. I'm going to set up for the next part of the question. So my domain and range, I start off with my parent function y is equal to the square root of x. And then I applied my vertical stretch by a factor of 3. A is equal to 3. That's what made this into my functional form, 3 the square root of x. If you notice, from my point notation right here, moving from here to here, what did we do to my x values, which is domain? We did nothing to them, so the domain stays the same. What did we do to the range? Well, we multiply all the y values by 3. So my range stayed the same as well. 0 times 3 is 3. Infinity times 3 is still a whole lot of infinity. Now, let's do the b transformation. So here, y is equal to 3, the square root, right? That b is right in front of that x. So what did this do? This reflected about the y-axis. And in point notation, it just simply, we multiplied the x values by -1. So we can almost just multiply our domain by -1. It changes the endpoints though. Zero times infinity is 0. 0 times -1 is 0. Infinity times -1 is negative infinity. And we've seen that in the reflection of the blue graph. Last but not least, thankfully we're almost done this question. Let's go to green. Now y or h is equal to 2. We're going to shift it 3 units over to the right. So I can just simply put my functional notation there, which isn't necessary. But if I'm going to shift this over to the right, my domain is I add 2, right? I'm going to add 2 to my previous x coordinates. So negative infinity plus 2 is still a whole lot of negative infinity. 0 plus 2 is 2. So that would be my domain. My range still remains unchanged. So there you have it. So just thinking about transformations, you can easily put together what is the domain and the range. I hope this helps. Ask questions.